Hi everyone. What I've got here is a simple frequency counter. You can see the display of the frequency on this. Made from a single microprocessor. This is an ATmega 328, the same microprocessor that's used in, or microcontroller that's used in the Arduinos. I chose not to use the Arduino. I have my reasons for it. I like to use my own hardware. And I also like to use a different development system, but this is my own development board that I've put together for my own use, and I just do a lot of development on this kind of thing. I can plug into the wires into the different I/O pins on the microcontroller, much like an Arduino as well. Over here is a in-circuit serial programmer that's made by Atmel. Atmel is the same company that makes these chips. And I just burn my code directly into the microcontroller rather than going through a bootloader. That's what Arduino uses. But anyways, I have created this frequency counter. It was an idea given to me by someone who posted some comments on my previous video on using a Hall effect device for measuring the RPM of a shaft by detecting a magnet spinning along on the shaft, and he thought that he'd be able to use that kind of a setup to count frequencies, but it's not the best way to do it. And so I've implemented a frequency counter using a different method with the ATmega 328 here, and I'll delve into the software in a bit here. What's shown here, or what's sitting here on this breadboard, is a transistor circuit to interface the signal coming in on this wire here, which actually is just a sine wave from a frequency generator that I also built myself, and it just cleans up the signal and shapes it so that the microcontroller can read it through this wire here, and I've got a scope hooked up to it as well. So I can show you a couple of things here. Over here on my workbench this is another frequency counter that I made some time ago. It uses a microcontroller as well. It uses the same method actually. It's a different microcontroller. There's some limitations with the Atmel device in how high a frequency you can detect. This one uses a microchip pick part, which implements its counters in a different way and enables you to detect a much higher frequency. And this one here can actually go to about 50 megahertz, whereas the one that I've built here with the ATmega actually can only go to about half the maximum frequency of the main oscillator, and I'll explain the reasons for that. And then I'll just quickly zoom over to the oscilloscope here and show you. There's the signal. So this is the signal output from the transistor, and it just it limits it to well, it's actually 4 volts. 5 volts is about here, and to ground. The signal coming out of the frequency generator, the signal generator, is actually plus and minus. It actually goes to the negative as well, and I have to be able to cut that off and shape it a bit so that the microcontroller can actually detect it. So that's a quick rundown on the hardware of this simple frequency counter, and let's look at it in more detail. Let's have a look at what's required to implement a frequency counter. And this is pretty much what you're going to see in any kind of bench type frequency counter. For example, the HP 5300 series type frequency counters, they're all going to operate pretty much the same way as this. And the main part of the frequency counter is this. It's a counter. What it is a special register that when you pulse it on this input here, it simply increments the value that's in the register. And also that register can be cleared. You can write zeros to it. And what we have here is a gate, and this is, if anybody understands digital logic, this is an AND gate, as I've drawn the symbol here. And the way this gate works is if either one of these inputs is low, nothing's going to come out of the output here. It's going to be always at 0. So you apply the signal to one of the inputs here, and it's pulsing up and down, and then you apply a gate signal from a pulse generator that goes high for a period of time. And when this pin is high, then the signal can go through the gate and into the counter and start incrementing the counter. And when the timer times out here, the counter stops incrementing, and the value of the count that you have in there can be used to determine what the frequency of the input signal here. And the simplest way to do that is if this time period that this gate was high, or that the gate was actually open, is exactly 1 second, and the counter starts off at 0, whatever count you have in the counter at the end of the 1 second will equal the frequency in hertz, or cycles per second. And in a benchtop type counter, the output of this counter register here will be decoded and put onto a display so that it gives you the value of the frequency in hertz, or whatever it is. And there'd be some more stuff going on here that would control the pulse generator here, turn it on, or give it a signal to start the pulse, and then another signal here to clear the counter in between counts. And so what you would see on the display is every second the display just updates. It changes. If the frequency isn't very stable, you'll see the display that would change every second. And this gate time can be changed. If you say made this gate time 1/10 of a second, then the cumulative count here would be 1/10 of this frequency, and you simply multiply this value by 10 before you display it. You're going to lose the resolution of 1 hertz. It'll only have a resolution of 10 hertz in that case. And so, but in this case, the display would update much more rapidly than in the case when this time here was 1 second. And these bench type frequency counters would implement all of this stuff here with high-speed digital logic. And if they do have a microcontroller inside them, the microcontroller would just be the user interface. It would read the push buttons and on the front panel that the user pushes to change the way the counter operates, and perhaps even decoding the value that's in the counter here and putting it up on the display, and maybe just the general overall control of this system. But all of this stuff here would be done in high-speed digital logic, and this pulse generator would be generated from a very stable frequency source, so that this time period is accurately known to probably less than 1% or something like that, and that gives you the accuracy that you need for this counter. What I'm going to do here is show you how to implement something like this with a microcontroller, but using the internal timers and counters to duplicate some of this. There'll be one counter duplicating this part here, or this part here, and another timer counter that will duplicate this part here. Now the ATmega 328 has 3 timer counters, 0, 1, and 2. And they all operate in a very similar way, and I've drawn a very super simplified diagram here of how each of them works. They are far more complicated than what I've shown here, because they also, all 3 of them can generate pulse width modulated signals on I/O pins, and there are a lot more peripheral, or a lot more components to the timer counters in order to do that. I'm going to use the timer counters in their simplest mode, where they simply increment the counter register through some source. And so this counter register is the same as what I had drawn previously in the frequency counter, which is this part here. And so I'm going to use these registers, or I'm going to use 2 timer counters in a very similar manner to what I just previously described for the frequency counters. So this register can be incremented, it can also be decremented, but I'm only going to use it in the increment mode. And Depending on which timer you've chosen, this register could be 8 bits or it can be 16 bits. Timers 0 and 2 are both 8 bits, whereas timer 1 is a 16-bit register here. And this register is connected to the data bus inside the microcontroller, so I can write to it and read from it as well. Now to clock it, I have a choice of where I can get my signal from. I can get a clock signal from the main oscillator, which is driven off the 16 megahertz crystal, which is used in the Arduino boards. Most of them are 16 megahertz. My own development board actually has a 20 megahertz crystal in it. And so this is the main oscillator that runs everything that runs in the microcontroller, and it's humming away at whatever the crystal frequency is. And it can go through a prescaler here, which is just simply a divider, and it can divide this frequency by 8, 64, 256, or 1024, and that's selectable. You can change that with the software. The output of this will be a frequency that is divided by whatever you've selected here, and it goes in. And this selection port here also is under software control, so you can determine whether you're selecting the clock for the counter from the prescaler, which just continuously runs, or you can select it to be an external pin on the microcontroller, an I/O pin. And timers 0 and 1 have pins T0 and T1 that can be selected to clock their respective registers. Timer 2 is done a little bit differently. You use 2 pins and you hook up a crystal to it, which is generally a lower frequency crystal than this one here, so you can clock it at a slower frequency. Often a 32.768 kilohertz clock crystal, which is used for real-time clocks, can be used here. So you can have a built-in real-time clock using this timer counter 2. What I'm going to do here is I'm going to use timer 2, and I'm going to select the prescaler here. I'm not going to use the external pin, and I'm going to select the divide by 1024. And so the main frequency in my case is 20 megahertz divided by 1024. So that gives me a pulse here into the timer counter every 51.2 microseconds. And that's what I'm going to use to generate the 1 second gate signal. And then I'm going to use timer 1, which is the 16-bit timer, as my counter, as I described as I described in the frequency counter, how they're implemented. And I'm going to select not the prescaler, but I'm going to select the external pin. And this is where the signal that you want to measure the frequency of is going to come in, and it's going to tick this 16-bit register every time there's a rising or a falling edge on the input signal. And I can also read that register when my gate time has expired. Now, there are a couple of considerations here when we're using these timer counters. And first of all, let's look at using timer 2 as the 1 second timeout. Now, even at a much slower frequency here, going in and clicking this counter over, an 8-bit register will require 256 counts before it overflows. And what that means is it'll count up 0, 1, 2, 3, 4, etc., and its maximum count is 255, and then on the next tick it'll just become 0 again and start counting all over. And that's called an overflow. But even at this divided frequency, which is much slower than the 20 megahertz, it's going to overflow very quickly, much less than 1 second. So what I have to do is count the number of overflows that this timer goes through to give me 1 second. And if I do a little bit of math, I find that there are 76.39 overflows of this counter in 1 second. So what I do is, in software, I create another counter, which is just a memory location in RAM, and I put 76 into that memory location. And then I enable the overflow interrupt for this timer 2. So every time it reaches 255, it generates an interrupt. In the interrupt service routine, I simply decrement that counter that started at, in software, that started at 76. And when it reaches 0, I know that I've 1 second has expired. And then I can stop the other timer 1 from accumulating the count. So that's a very rough description of how I am using timer 2 to generate the 1 second gate time. Looking at timer 1, instead of, like I said, instead of using the prescaler here, I'm now clocking it from the I/O pin, which is actually the signal that I want to measure the frequencies of. And there's a couple of considerations here with this one as well. A 16-bit register takes 65,536 counts to reach its maximum, and unless you're measuring frequencies that are less than 65 kilohertz, 65,000 hertz, this register will also overflow, much like what I said the timer 2 will do. And so I also set an interrupt, or allow this to generate an interrupt when it overflows as well. And every time it overflows, I increment a register in memory with software. And so this counter will be busy humming away, counting the signal that you're trying to measure the frequency of. Every time it overflows, it increments another register. And at the end of the 1 second, this timer is turned off. And then I take the software register and the value that's in this register, and I combine the two, and I create a much larger number that gives me the total accumulated count in the 1 second window. Now, and again, that's not hard to achieve, but it does require a bit of overhead in the software. The other, there's a caveat with this timer, and it's the way this pin is interfaced into the counter. It is going through a chunk of electronics, which I haven't drawn here, that synchronizes this signal with the main 16 or 20 megahertz crystal. And only when it has detected that edge based on the synchronization logic will it then increment this counter. And the problem with that is that the maximum frequency that you're allowed to apply to this pin and still have it reliably clock this counter is defined in the spec for this microcontroller to be the main crystal frequency, whatever it is, divided by 2.5. So with a 20 megahertz crystal, the maximum frequency I can reliably count on this pin here is 8 megahertz. And with this 16 megahertz main oscillator, it's something like 6.8 megahertz, I think it is. I forget. I worked it out, but I can't remember the value. But it's significantly less than the value of your main oscillator. So if you're wanting to measure the frequencies of higher frequency signals, you will have to do something outside here and divide it down, much like I described the prescaler here, and then do some math in the software to do the calculations to figure out what the frequency is. But to the maximum frequency applied to this pin that you can reliably measure is about 8 megahertz if you have a 20 megahertz crystal. So that is a very quick description of how I've implemented the two timers to create or to implement a simple frequency counter. Now earlier I mentioned the transistor that conditions the signal before it goes into the microcontroller. Well, this is the schematic of it here, and this is just an ordinary 2N3904 transistor. You can get them anywhere. You can get a bag of 100 for a few cents each, so they're pretty cheap, but they're very versatile transistors. I use them a lot in various things. They can be used as a switch, or they can be used as an amplifier and like an analog device here, which is what I've done here. This circuit is required because the signal input could be of varying amplitudes. So this provides a bit of gain, and so that there's a big enough signal coming out here that goes to the microcontroller. The input signal may or may not have a DC offset on it, and so I put a capacitor in here to filter out the DC offset. And this resistor here just gives a bit of negative feedback so that the amplifier is stable. And also I can just plug in any transistor in here and this amplifier is probably going to work. The gain of each transistor here is a little bit different, and this feedback here just kind of takes some of that out of the circuit so that it'll still work with transistors of different gains, current gains. This is the load resistor. Without it you wouldn't get a signal. And this resistor I put in here, it sets the bias point on the collector here, and it brought the collector voltage up to about 2 and a bit volts. Without it, this signal never got high enough in voltage to trigger the microcontroller. By putting this in here and changing the bias point of this circuit, I got the circuit to work better. This diode here I put in with big signals applied to here. This point here can actually go negative, and I don't want a negative transition going into the microcontroller. They don't like that very much. So I put in this diode here. It's a Schottky diode, and you can look it up, and I won't go into any details about what a Schottky diode is, but the main thing about this diode, it has a much lower forward voltage drop than a regular silicon diode. And so it keeps this signal from going too far negative, and it protects the input to the microcontroller. And so that's what that little transistor circuit looks like. It's easy enough to build. These are just ordinary quarter-watt resistors, 5%. They're nothing special. And but you're going to need something like this on the input to the microcontroller. Unless the signal that you're actually measuring the frequency of is already a TTL signal that goes for between 0 and 5 volts, then you won't need all of this. But often, you might want to measure the frequency of signals coming out of a radio or something like that, and so they're going to be quite low level, and they may be varying between some negative voltage and some positive voltage, and so this capacitor helps to take that out, and the transistor will still work. So anyways, I put this in here because my signal source was actually quite small and wasn't enough to trigger the microcontroller. So that's a quick look at the interface circuit to this frequency counter. And I thought I'd just show you very quickly here the frequency counter that I showed you earlier in the video, and the inner workings of one that I built a while ago. It's a little bit more complex what I've done to it, and the complexity is sitting here on this board, and this board here kind of duplicates the circuit down here, but with more capability. And you see a potentiometer on the front here. With this potentiometer I can change the gain. I don't know if you can see that very clearly, but there's a number of transistors in this circuit here. This is just a piece of ordinary double-sided printed circuit board, raw, unetched, and then I just solder little bits of circuit board, or glued them down actually, onto the board here to make interconnects between all the components. Some places the components are actually soldered right to the board. This is where the ground, because this circuit board here is the ground plane. And anyways, the signal comes in here into the circuit, gets conditioned, gain is adjusted with this potentiometer, and the output is here, and it goes into the microcontroller here. And all the protection, kind of what I've done here in this circuit, is all in here. And so the signal reaching the microcontroller is already limited to 5 volts and ground. This box actually has a dual purpose, and I won't go into too much detail. Inside here is something called a directional coupler, and there's 2 connections in the back for RF cables. And I use this box also to measure the power coming out of my radio transmitter. I'm an amateur radio operator. And also to measure the reflected energy that comes out of back from the antenna if the antenna is not properly tuned. And that again gets displayed on the front panel here. And the circuitry that does that, most of it's inside here, but pull this cable out of the way. You can see that chip there, that's an op amp, and there's the circuitry around the op amp. And you get two signals coming out of this, one for forward power and one for reverse power. And then I just bring them into the A to D converter on this microprocessor and read those signals, and then I can display the SWR, the standing wave ratio. Basically just it's a measurement of the amount of power being reflected back from your antenna when it's not matched properly. And it displays it on the screen here, and then there's all these push buttons so I can change the functionality of this box. But just a quick look at the inside of a frequency counter that I built before. Also, I thought I'd give you a quick look at the inner workings of my signal source. This is how you change the frequency of it. It goes from somewhere around 2 megahertz up to about 30 megahertz in two ranges. This switch here selects the range. Down is the lower range, I think it's 2 to 10 megahertz, and the up range is about 10 to 30 megahertz. And the circuitry inside is built in the same manner as I just showed you with my frequency counter. This is just a big chunk of raw circuit board as well, and all the components are attached to little bits of circuit board stuck on top. And this is a tuning capacitor here, a variable capacitor. As you rotate the capacitor here, the plates go in and out, and it changes the value of the capacitance on these two different these are actually two separate capacitors that are just tuned together. And one goes to one oscillator, which is here, and the other oscillator is over here. And each of them are running independently, and just flipping the switch here turns one or the other on. And then the outputs of the two are combined in this circuitry here and conditioned and amplified a couple of times. The power amplifier is this transistor here, and then the signals come out to the two jacks here in the front. One of them is an attenuated output, and the other one has got a little bit more signal to it, and that can go into one of them will go into a frequency counter, while what the other one is being used to drive something in your circuit. I would use something like this for perhaps tuning some circuits in my my radio, or if I'm building a radio, which is something that I do as an amateur radio operator. I'm allowed to build radio equipment as well, and so having a frequency generator like this is very useful for testing and building radio equipment, receivers and transmitters. So another quick look at another piece of electronics that I've built. At some point down the road, perhaps I will produce a video on how this was built or something like that. It all depends on my time, and then maybe I'll produce another video on how the directional coupler that I made that goes along with the frequency counter that I made. Maybe I'll do another video on how this stuff was all put together as well. But again, it's all to do with how much time I've got. Now, I've split this video into, or this frequency counter video into two parts because it was getting pretty long. And so this is part one, and part two will cover the software, and we'll get to that bit later. And I'll post them, they'll probably go up within a week of each other, so you'll be able to have both videos together. So anyway, stay tuned for my video on the software. So thanks for watching, and if you guys enjoyed this, please give me a thumbs up on the YouTube, and if you're first time here, please subscribe. I'm trying to build up my channel. There's a few people that are still getting a few subscribers, but the more the better. So anyways, thanks for watching, and I'll catch you the next time. Bye for now.